So we have learned about AC power source connected to a resistor, that AC power source connected to an inductor and connected to a capacitor. And we have also learned about phasor diagrams. Now let us see one more numerical, this example 7.4. A 15 microfarad capacitor is connected to 220 volt 50 hertz power source. So since hertz are given, that means it is AC power source. Find the capacitive reactance. So we have to find XC and current RMS and peak, both currents, RMS and peak currents. If the frequency is doubled, so what we are doing, we are doubling the frequency. What happens to the capacitive reactance and the current? So what will happen in that case to capacitive reactance and current, that we have to tell. So first of all, we calculate the what is the capacitive reactance. So capacitive reactance Xc is equal to 1 upon omega C, and omega we know that is 2 pi mu and this is C. Let us put all the values. So 2 pi, this nu is given as 50 hertz and this capacitance is 15 microfarad. So 15 into 10 to power minus 6 farad. When we calculate, we get Xc equal to 212 ohm. So this is a very similar to resistance which hinders the current in flowing. So this is 212 ohms. Now we have to calculate what is the IRMS current. To calculate IRMS current, what we know, we need the voltage, IRMS voltage divided by this capacitive reactance. RMS voltage is 220 volt divided by 212 ohm. So after calculation we get this is 1.04 ampere. Now what is peak current? So we know peak current is under root 2 times of IRMS current. So under root 2 is 1.41 and this IRMS current is 1.04 ampere. So peak current would be 1.47 ampere. So that means this current oscillates between plus 1.47 ampere and minus 1.47 ampere, and this current is ahead by voltage by pi by 2. This current is ahead of voltage. So this is current. So this peak is plus 1.47 ampere and this is the minus side peak. This is minus 1.47 ampere. And there is somewhere IRMS current. Now what will happen if we double the frequency? So this was the formula, Xc is equal to 1 by omega C. So what will happen if we double this frequency? So previously this was 2 pi nu and nu was 50. Now we are doubling this to 100. So what will happen? So when frequency is double, capacitance reactance is halved. If we double this number, this reactance will be halved. So previously we get 212 ohm, then it will become 106 ohm. Since reactance is halved, so current will increase to double. Reactance is now 106 instead of 212, so current will be doubled to 2.08 ampere. Let us see this one more example. A light bulb and an open coil inductor are connected to an AC source through a key as shown in figure. So here is our inductor, this is our light bulb and this is our AC source and this is key. So with the help of this key we can switch on the current or switch off the current in this circuit. The switch is closed and after some time the iron rod is inserted into the interior of inductor. So now what we do, we switch on, this switch is closed, that means power is on, and we put an iron rod inside this inductor. Interior means inside. The glow of the light bulb increases, decreases, is unchanged as the iron rod is inserted. So this is a multiple choice type of question. So we have to tell whether the glow of the bulb will increase or decrease or will remain unchanged when we insert the iron rod. and we also have to give the reason. So this is a multiple choice of question: increase, decrease or remain unchanged. So we have to tell. So answer is, when iron rod is inserted inside this coil, the magnetic field inside the coil magnetizes the iron. So we have also learned that when there is a coil and we put some ferromagnetic material inside, so this material also magnetizes with the help of this coil. So this magnetize the iron. So this will, what will this do? This will increase the magnetic field inside the coil. So this insertion of this iron rod will increase the magnetization inside the coil. Hence the inductance of coil will also increase. This will increase the inductance of the coil. Consequently, the inductive reactance is omega L. Since L is increased, so XL will also increase. As a result, a larger fraction of applied AC voltage appears across the inductor, leaving the less voltage across the bulb. Therefore, the glow of the bulb will decrease. Let us understand it another way. So we know, as we insert this iron rod, the inductance of this rod will increase. So magnetic field will increase, and magnetic field will increase the flux because current is same. So let us see, we know that when we insert the iron rod, this magnetic field will increase. This magnetic field will increase. When this magnetic field increase, this phi b, that means flux will also increase. Flux is increased, this b in dot A, flux will increase, and we have seen this phi b and phi was L into I. L into I, since current is constant, so many times increase, this will increase many times, phi increase in many times will increase the inductance. So now inductance L is increased because B is increased, phi B is increased, phi is increased, L is increased because current is not changing much. Now let us see what is the effect of this L increase. Since we know XL is equal to omega L, so L increase will increase XL, so XL is increasing. Now we see this is a series circuit, so this is XL, this is R. If XL is increasing, total resistance of the circuit is increasing, that means current in the circuit is going down. XL increasing, total resistance of the circuit increasing because R is fixed, but XL is increasing. So current will go down. If current is low, the glow of bulb will decrease. In this way, we can understand this problem. Insertion of iron rod will increase the magnetic field, that will increase the magnetic flux. Magnetic flux will increase the inductance of this coil. Inductance increase will increase the inductive reactance, and if inductive reactance will increase, this is a series circuit, so XL plus R is total impedance of the circuit. This we will learn what is this Z. So total resistance of the circuit will increase, hence current will go down. If current goes down, the glow of the bulb will decrease. Now we have just left this point. Let us understand why there is no power consumed in when we connect an AC source to a capacitor by charging or discharging. So let us understand this. This is very similar graph that we have learned in case of inductor. But here difference is that we are starting with current. So initially current is at peak, voltage peaks after T by 4 time. So every slot is T by 4. Every slot in time is T by 4, and this total is 2 pi. So this is pi by 2, this is also pi by 2. So every slot is, in terms of phase, is pi by 2. Total difference is 2 pi. Total time is T. Every slot is T by 4. Now we have to understand why total power consumed in a complete cycle for a capacitor is 0. So in case of capacitor, we are starting with current. So this is current. So current, we have learned that current is ahead in case of capacitor of voltage. So current peaks at 0. Current is peaking at 0 while voltage is peaking at T by 4. So there is a delay in voltage. Voltage is lagging. Current is ahead. So let us understand with 9 different points. So first point is that here what we see at first point current is maximum, positive and maximum, but voltage is 0. So power consumed, power is V into I. So power consumed is 0. When we see at this first point, so current is 0, voltage is maximum. So current is 0, voltage is maximum. Again power consumed is 0. Let us see at this point 2. At this point voltage is again 0, current is maximum but in opposite side. So minus Im into 0. Again power consumed is 0. Now let us see at this point 3. So at this point we see current is again becoming 0, voltage is negative but on other side, minus Vm into 0, that means 0. At this final point this voltage is again 0, voltage is again 0, current is I max. So we have come back at the first point. So at all these points power consumed is R0. Now let us understand what is happening at points in between. Let me mark them as point 5, 5, 6, 7 and 8. So when we see point 5, so at point 5 there is some positive value of voltage, some positive value of current, that means there is some power. So V is positive, I is positive, so we get positive power. That's why some power consumed here. So power is here positive. At this point it was 0, at this point was 0. These points were 0. Now let us see at point 6. At point 6 what we see, the current is negative, it is minus I, and voltage is in positive. So V is in positive. So what we get? Negative power. That means power given by the capacitor. At this third point, if we see both current and voltages both are negative. So what we get? Negative, this was negative. So both are negative. Voltage and current both are negative at this point. Both are in negative. So we get again power consumed. Negative, negative cancelled out. At this point 8, so what we see at this last point? At this point we see this current is again positive. This current is going to be positive, but voltage is still negative. So minus V into positive I, we get minus P. So total power consumed in this cycle is plus P minus P plus P minus P, that means 0. So in this way we learned that average power consumed in a complete cycle by a capacitive circuit is 0.